Okay, so today I'll be talking about quasicrystals, methods to generate them, so the multigrid method and the cut and project method, method for generating empires, both in the multigrid and cut and project, and I'll talk about cut windows and vertex types, and I don't know, just gonna start and see where it goes.
You need two chairs.
Where's the, oh, there.
Oh my God.
Multigrid. So the idea here is to take a space and then start inlaying it with parallel hyperplanes. So you'll have a grid here dictated by a normal vector, and you'll map the grid lines using this equation. So just starting from this point, going in this direction, integer multiples outward. And then you can take this grid and translate it forward and backwards using a shift vector, shift amount. So you'll have one shift amount for each grid that you're dealing with. So for the Penrose, you have 5 grids oriented in 1/5 rotation all the way around. So you have a pentagon of grid vectors.
I have a question.
Yeah.
So if you shift one of those classes of parallel lines, you break the H2 symmetry, and I'm wondering if you can still recover using the dual grid method. Once you've broken the symmetry, can you still recover the Penrose tiling using the multi-grid method?
I believe so.
Yeah, the shift vector just get a face-on flip, really.
Because if you shift, one of the parallel line classes, you break the H2 symmetry. So
Yeah,
I guess
but
that's.
you break it in a grid space, but really in the Penrose space, you
don't
still
need
have the same.
Yeah.
Yeah, the dual
Yeah.
and the grid space, they're not like they're topologically kind of a dual, but
Yeah.
not really
Okay.
exactly, they're
Right.
mapped at the same place.
Yeah. So they're not isomorphic to one another. They're just
Right.
analogous.
No, and in a way there are, but
I mean, isomorphic means you have to have a full, absolute one-to-one.
yeah, it is. It is. It's just like in the dual, like when you take the dual, it's like the raven thing. It wiggles. It's not straight.
Okay.
Yeah. So, so you have these grid lines, and the grid lines will create, a grid pattern, and the grid lines are indexed by a number. So this grid line is 1, and then the next one up is 2 or 0, -1, that kind of thing. So each one has an integer associated with it. And so the procedure is to take the spaces in between are numbered also in each grid. And whenever you have a little region, these mesh regions, these white regions that lie away from the grid lines, each one is contained within 5 of these slabs, these stripes. Each stripe is numbered, so each mesh region is assigned to 5 integers as a coordinate. A tile will form on the vertices. Whenever 2 grid lines meet at a point, the point, you take the dual to a point, the point will become a whole tile. So you will go around a point and look at all the mesh regions that are adjacent to that point. Those will give you 5 vertices in Z5, and you take that integer sequence and then you just take that integer combination of grid vectors, and that'll give you a point in 2 space. So yeah, like 1 times the first vector plus 2 times the second vector times 1 times the third vector. It will give you a point. So you follow those prescriptions around, and that'll generate these vertices here, and make a. Were you about to say something?
Oh, I just saw like you already shifted the tile.
Oh yeah. So we can look at what happens when we shift the vectors around.
Can you want to make that larger?
Yeah,
Oh,
did
yeah.
you see when he moved the grid? When he moved the grid, he just shifted the ribbons around.
Huh.
No, you can show more, because
show more.
I think what you just showed is really interesting.
Yeah.
That whole ribbon, basically that blue ribbon, notice those blue ribbon, and then Dugan, can you move that one? So the blue ribbons will just move. See? To move to the left and to the right.
Oh, that's neat.
Yeah, but it does not change the whole symmetry.
Right.
It's at the center, the fivefold is no longer at the center, but it's still fivefold.
It's
general.
somewhere.
Yeah.
It's just not at the origin.
Oh, hold on, Dugan. So Fong, I wish that I kind of know why me and you and Dugan probably more than the others understand a little bit more deeply about the motivation for this, because we understand the history of the dual grid method that you did, and I have these, do you think it would be helpful for everybody as they hear this to hear you give a kind of overview of the motivation as to why this is relevant, the dual grid method, to deeply understanding the very construction, of the QSN, or is that not even helpful?
Yeah, I mean, I can give maybe next time I can, because next time I'm gonna talk on QSN. Maybe before my talk, I can just give a little bit.
I usually like before talks for everybody to kind of give an overarching motivation so that they can follow and relate it into somehow what we're doing here. So I'll attempt it really fast, which is what we're doing here is deeply related to the dual grid method, because the way that we discovered how to construct the QSN, and later we discovered all these powerful code qualities of the QSN, and we never knew that it related to E8. We only discovered that after we created it. So she really just kind of applied De Bruyn's dual grid method, which is the induction of the Penrose tiling from this process Dugan will show from a class of crystals. So you just have a parallel set of lines, and you have 5 of them. You can do the same thing with Z2 tilings. Another just checkerboard, same thing. And you can derive it. Anyway, then she did that, and then we realized that the way that we put them together created planes that intersected, and where those intersection points occurred, it started.
You're talking about the QSN, right?
Yeah, it started.
10 plane sets.
Yeah, 10 plane sets, but the dual grid method applied. This method applied to 3D, and then it automatically created intersection points that generated regular tetrahedra. And it turned out that the regular tetrahedra were organized as these objects that were 20 groups that we discovered back 9 or 8.5 years ago, with this golden ratio angle that comes out of the relationship of tetrahedra from E8, right? The arc cosine 1/3 angle minus arc cosine 1/2, right? 15.52 degrees. Anyway, so it just got deeper and deeper, and we started just getting luckier and luckier as all these things materialized. But it all came from an application of De Bruyn's dual grid method to a 3D case. And so perhaps,
And the dual grid method is kind of like a sum of waves.
Right.
Which is deeply related to
this,
the
yeah, and then one more thing, which may or may not be true, is I always think in the dual superposition of the idea that the QSN is deeply about the combination of regular crystal shapes, such as cuboctahedra and tetrahedra and cubes, with the regular H3 symmetric shapes. And they live in one system together. And similarly, if you think about the dual grid method, it's really like taking periodic or crystal-related things and finding the hidden encoding through the dual grid method of the higher symmetry thing. So.
Well, what would happen if I put everything to 0? The shift vectors. Would that make a periodic set?
No.
I don't think it would be a valid tiling.
No, it's either Penrose tiling or generalized Penrose tiling.
Well,
You're gonna have the illegal tiles, but it's legal in generalized Penrose tiling.
it's legal if you allow it.
See, you have the 10 paddles in the center, very center. You have the 10 thin rhombs. That's not legal for Penrose tiling, but in generalized Penrose tiling, it's still legal.
Right.
Would that be the only one in the tiling?
No,
Well-
no. You can see it
Oh,
everywhere.
there's another one, yeah.
In the center, for
Oh,
example,
oh.
there is one which is illegal.
That's when Dugan in the Cartan project method, if you do the shift vector to be half instead of integer, I think, like, or the other way.
Oh yeah, you have to shift by a half.
Yeah, if from the true Penrose tiling, and then you get this.
Mm-hmm. So when you just do a little animation here, you can see kind of glitchy patterns that arise as someone gets flipped. Here, let's try this.
Dugan, you can't, with how you've set it up, you can't simultaneously move two of those, right?
I can.
Oh, right, you can just
You
play
can
both.
start running it.
Oh, so I wonder if that makes a lot more interesting.
So each time he moves, we see one line parallel to one of the.
Yeah, that line is
Directions.
like a whole flip.
It's a hop flip.
Yes,
Yeah.
left and right flip. And
Yeah, if you see two lines at once glitch, that means that there's someone in the center who flipped, and he sends out rays.
Can you zoom in?
And usually those lines form pretty
control.
nice Fibonacci chain, like more regular than others. When there is a flip.
It's fast, so we cannot see if there is only one line moving or two, but I see only one.
Well, one at a time, depending on the step. You know, if you make a super small step, then it's just a one.
Sometimes it,
Well, I think that if you see, a 1 bar flip, that means that someone up there, he has like 3 bars coming out of him, and you're only seeing one because he's so far away. Like he could be anywhere in the.
I see only one when it's outside of the window, the thing which is moving.
Okay, let's talk about empires for multigrid before I move on to the other ones. So you have lines, and 2 lines will intersect to make a tile, and then you can ask, how stable is that tile under like perturbations of the shift vector? Okay. So this point here corresponds to this guy, and his point is really close to this line. If I move this line down, it would cross that point and it would change that point's its integer coordinate. It would bump up a coordinate. Whatever shift vector this is, on one side it's 0 and on the other side it's 1. So right now this guy is registering a 0 coordinate for that grid. If I move that grid down, then all of a sudden this point is registering the other side of that. Anyway, he moved. The blue one moves precisely when that line goes over that point like that. and then subsequently he'll
It's all
move in
about the
chunks as
order
the.
of the cross section.
Mhm.
That's when Amrik and I were talking about this matrix thing. We were considering the order of the intersection.
That's a pretty good Mathematica file.
Yeah,
Yeah.
good job on that.
That's a good job.
So to ask how much wiggle room does a certain tile have in the grid lines? Okay. So like our guy was here, right? So he has like this much room between this vector and so much room between this vector and that vector. And, he has a little neighborhood, one in each direction for each grid vector, and that kind of represents a little volume in 5 space of his wiggle room. When you have more than one tile, you collect a bunch of tiles and you ask collectively between all of the tiles that I have, between the 3 of them or 5 of them or whatever you want, you ask how much wiggle room does it have and how much wiggle room does he have, and you take them all together and you say together they will all stay stable under this amount of perturbation for the shift vector. And so that'll give you, empire window. No, that's not the
But
right
wouldn't
word.
the shift vector, couldn't you connect that perturbation of the shift vector to be bounded, restricted by an empire window that you impose?
Same
Yeah,
thing,
that would be
it's just
the-
it's a valid set. Here they call it a valid set
Right.
instead of empire window. So yeah, it's
Yeah.
the wiggle room.
Right.
But basically, yeah, it's the
Yeah.
same concept, and it's isomorphic. So you're really dealing with a volume in 5 space of possible shift vectors that you can use to keep these tiles intact.
So how would you, because it seems to me that you can, but how would you connect, maybe either of you can answer, how would you connect the sum of waves principle, which seems very interesting physically, to all of the group wiggle possibilities here? In other words, this sum of waves way of understanding quasicrystals has always been interesting. So how would you?
Well, sum of wave is literally taking the grid space, right? So the wave are periodic.
Mm-hmm.
And then so we're looking when one wave is moving up or down, just as you showed there, when you just move one set of parallel lines, there is a crossing thing. And so that does seems like a flip.
And then you
also.
could take the sum of waves as periodic sine waves, and you can convert that to a set of Fibonacci waves, and then you could cut out
And that's
the
a
dual group.
quasicrystal.
And then, but
Yeah.
dynamically, you can see the sum of waves, and that should give you all of the.
Yeah. Yeah, I mean, if you look at the Penrose
Yeah.
like each of the ribbons, if you take each of the ribbons as a wave, right? And so that is, Penrose is a sum of periodic wave, really. You see those blue lines, they're
Yeah.
periodic. It's just like the wiggle,
So
because they have to wiggle around to.
right. So would you agree that all of the finite set of shift vector positions are describable as Dirichlet integers? Or
No,
no?
it's more of a.
Oh, it's an integer
It's
thing
no,
because that's the shift vectors
The
are
shift
on the
vector is
hyperlattice.
not integer.
It can, yeah.
It's
It
a
could be a- it
continuous
can-
domain,
It's
It's-
a range of a continuous.
but maybe the boundary are directly integer.
It's not continuous because actually, or is it?
It is.
It is.
It's a continuous region.
But though the change is discrete.
Yeah.
Like you
The
can within
boundary is-
certain
Yeah.
range there is no
Yeah.
change, and then
Yeah.
it jumps and then
Uh-huh.
jumps. Yeah.
Yeah. So it's like.
Oh, no, it's not continuous because as a shell model of projectors, the further you go out, the closer the distance is between the successive shells that can capture
Yeah.
your
I'm saying like
discrete
you can
points.
change the window continuously, but the change, the resulting change is discrete.
Yeah, this change will always be discrete, but if you use ring projectors, what happens is as you go out further and further, you move smaller translations of your discrete, so it shrinks.
Yeah.
Yeah.
Yeah, I think what you're getting at is when you zoom out, look at the lines and look how close they get to each other. And so, yeah, under perturbations, I have a lot of wiggle room before one line crosses another point or something like that. Unless I zoom out and look at more of the picture, and then I ask, okay, well, what points are like close by other points? Like, you know, this cluster here,
You make
very dense.
like you make an acceptance domain, and then those domains where there's almost crossings, they have the full symmetry. Like we talked about that about a year ago, where you can just take one of these grids and you can actually just select an acceptance domain and say, well, if they're close enough, I'm going to circle those, and then I'm going to make those points or something. And because you'll see when you make a big one of these, you zoom out, and even before you do the dual grid, you will see, if you zoom out far enough, you'll see what looks like the Penrose tiling.
Okay. So what I was saying is, if you zoom in, you have a lot of wiggle room.
You can make a bigger change with a bigger shift without any changes. But
Right.
if you zoom out, a tiny bit of change would shift or change things.
Yeah, when you zoom out, now your wiggle room is less before you see a change within your viewing window. And basically, if you zoom out, if you look at the whole tiling as a whole, and you make any perturbation in the shift vector, there will be somewhere it'll make a cross.
Which will make a flip.
It'll flip.
Yeah,
So,
unless it's a finite, as Chris said.
unless it's finite. Unless you're looking at a finite subsection of the tiling.
Or unless your shift is not big enough to create a flip.
Or if it's an infinite lattice.
Then
yeah.
every infinitesimal one will have a, yeah.
Okay, so here's what happens when you rotate some stuff. Okay, that's trivial rotation. All right, so here I'm rotating dimensions 1 and 3. I have all the rotations for 5 space laid out here. So yeah, it's just changing the shift, the vectors which generate the grid lines, and changing the grid. And now we'll look at the tiles. So it's a very robust algorithm. And when you make one of the vectors long or short, you can kind of see in that direction things getting spaced out, like horizontally, for instance. So things getting bunched back together. Get all kinds of stuff. So you can have like really thin tiles and then regular ones.
Starts looking 3D.
Mm-hmm.
Penrose tiling is kind of.
Looks 3D, yeah.
Yeah, so this is Penrose tiling again, but with a height added to each
It's a layer of a three-dimensional
Yeah.
Penrose tiling.
So yeah, so I was going to say. So this shows intuitively how, when you project the Ammann tiling, the 3D Penrose tiling, it projects to the QSN. But in the Ammann tiling, the two-dimensional angles are rational, and in the Penrose tiling, they're irrational. So when you project the rational angles to the plane, you get the irrational Penrose angles right in your 2D.
Is this a part of an Ammann tiling?
The shingled roof
That's
thing you made
that's what
was
I just
a
said, that's a
surface in
layer
a
of the
Penrose, in a
tiling.
Ammann.
Oh, okay.
Yeah.
Yeah.
Yeah. If you keep the shift vector orthogonal to the tiling space, and you can kind of keep the center of the tiling at the center of the plane, and then just kind of watch everything flip kind of in place, you know. Once again, everything flips along ribbons. Yeah, and here each tile is identical now. Instead of having thick ROMs and thin ROMs, when you tilt them, you kind of unfrustrate them, I guess, in a way.
Yeah, they're the faces of the rhombohedron in 3D Penrose tiling.
So, multigrid. So you could do the multigrid in a three-dimensional setting or n-dimensional setting. For the Ammann tiling, you pick grid vectors, five-fold looking down, and then the z-axis as a sixth vector. So it's, I can't rotate this, but when you look from the top down, you see the pentagon of shift vectors. So you'd expect to see a lot of the same similarities between this tiling and the Penrose tiling. Yeah, so when you do that, you get your tiling with rhombohedron now. A rhombus is made out of two vectors that you add together to get a rhombus, and then if you have three vectors in space, then they form to make a cuboidal sort of rhombohedron.
So I believe here in the 3D Penrose tiling, your rational value moves to the dihedral angle, and your irrational value moves to the angle between the line angles.
I'm not sure what you mean.
The dihedral angle is the angle between planes, and the line angle is the angle between lines. So your Penrose tiling has your irrational angle between lines, and then your Ammann tiling has your irrational angle between lines, which which causes the dihedral angle between the facets to be rational.
Could be the case, I'm not sure.
That's true, Clee.
Yeah, and it's the same angles. So the dihedral angles in the 3D Penrose tiling become the same angles as the. Yeah.
Record this thing. Look at that. Enable.
Take a hit.
There we go. Oh, okay. This is. What?
I told it. No.
Take a
David's
hit?
just laughing because I handed the rose to Fong and said, "Take a hit."
Oh, I see. These are from the Ammann tiling. They're the vertex configurations of the Ammann tiling, and then I put something else for these.
Hey, look at that. You have the Wolfram logo up in the icon, and then you have the Wolfram logo right there.
Oh, yeah. I haven't seen that thing everywhere. So this is what an empire for the Ammann tiling looks like. Oh, I didn't even talk about empires for the Penrose. I started it, but I didn't finish. So you ask how much wiggle room a tile has, and you can get an answer. It's a valid set of possible shift vectors that keep that tile intact. You can take a patch of tiles and ask the same thing between the group of tiles that I have. What's the intersection of all their valid sets? You'll get a subset of, you'll get a smaller set of shift vectors that are valid for that group. And once you have that valid set, that wiggle room of lines, you can ask, what are the other tiles out there in space that remain unperturbed under all the perturbations that I can legally be allowed to do with my patch. So they'll be forced tiles.
The empire.
The empire, right.
It's okay to not show the 2D one because we have
Okay.
shown before.
Yeah.
You can go straight to 3D.
So here with, this is with 6 planar classes. I showed you the diagram earlier. empires
It's so
are.
pretty.
It really is
Yeah.
wonderful.
It is.
Way better than some of the other ones.
So don't be fooled by these all-sided layer, because those just because we don't have enough.
You might recognize the sun type, and then the other type,
Cartwheel.
cartwheel.
Well, that's not the cartwheel, but
And these are like some of the other ones.
that's like a cartwheel.
Yeah, it's made out of Penrose tiles, but it's all 3D. It's great. But yeah, some of these empires are dense and not as interesting as some of the other ones. But still, there's gaps in there. There are ribbons that run through the space. You can't kind of see lined up in a row, long and short sequences.
So if you thinned out the cut window, it would still show the skeleton of this empire more clearly, because you'd open up gaps so you could make sense of it.
Well, if you
you
thin
did
the
what?
empire window, it's no longer be.
Not the
it's
empire, the cut window. You thin the cut window, and then less points will come into your projective space, so that you could eliminate some of these points, so that you get a little bit sparser thing.
But why?
Oh, I was only saying, I'm not even saying you should. I was just saying if you did, you'd start to see a little bit more of the skeleton or substructure of this, because right now it's closed off to our view, because it's
But Dugan,
solid.
can you show the one that is? I think it's the first one
Mm-hmm.
that has only the rays coming out. I
Yeah.
remember those one.
Let's just call them Oshheims from now on. The Empire Oshheims.
These,
Oh, see
these,
this
huh?
one?
Yeah. So this guy doesn't do much. The smaller sets of tiles, the less tiles you have, the less restrictive you are. And so the less,
The less tile you have, the more restricted. Your wiggle room is very tiny. But you have high frequencies.
no, with a smaller tile set, your wiggle room is more.
So you have more discrete positions.
No, your wiggle room is less. Definitely less. That's why, because your wiggle room is so small. Oh, you're right.
Yeah, you have to think backwards.
It's opposite. It's different than the empire window, because if you have a narrow empire window, because your density is proportional to the window, your empire density. But here it's the opposite, because the more you can wiggle, that means the
Yeah.
bigger empire window. Yeah. Okay. So this is
Yeah.
like you can
Play
wiggle.
around, you can adjust that.
Yeah, you can wiggle more.
Yeah, so
So that's where I think that the scaling factor is going to be something we'll use on the projection operators, because it'll change the distance that the particles hop, which some energy landscapes will kind of statistically require longer range hopping, and so there you'll have that family up here of those sets.
Fong, talking about the wiggle room, if you have a small set of, if this is your empire valid set,
The wiggle room is it's the other part, the one that is not part of empire room, right?
right?
It's the these are complementary.
Here are the empires for Penrose.
Go full screen, Dugan.
Yeah, so here you can kind of see that it's carved out by those lines that you see when they flip. It's like I can flip all these lines, but the other stuff has to stay. So here it's a little less dense of an empire. But yeah, whenever you have the red guy in place, what has to happen is these green guys must be in place, and you can do whatever you want in between. So yeah, a question that Fong posed was, what are all the possible tiles? instead of eliminating the ones that aren't green, include, let's see how to say this.
Like when you wiggle the room,
Yeah,
and you want the possibility space, right? You want to say.
You look at all the tilings which keep the red one intact, and then take their union. And the green ones will stay as they are, but in the blue spaces you'll get like stacked up multi-tiles kind of on top of each other. So that's an interesting analysis.
And then Dugan, I want to keep reminding us that when we think about forcing, we have to always be aware there are three classes of states. There's the class of tiles which are forced off, the class forced on, and the class neither forced on or off. So it's three different kind of categories.
Okay.
And so the two classes that are forced, the class of forced on and the class that are forced off, are both in some sense the empire, right? The forced places where you just can't have in that, if that's your shift vector and that's your empire window, then that must be off and that one must be on. And then there's another set which can be on or, well, it can be on or off if you move to a different shift vector. So the window, obeying the window as your boundary, defines your on and off ones as your empire, and then gives you freedom, your syntactical freedom, right, as the ones that are neither forced on nor off.
Yeah. So then, in this case, like the green are the forced on, and the blues are, can be on or off. And the one that is forced to be off is not in this picture, basically.
Let's move to cut and project as a different method for creating quasi-periodic tilings. So everyone's seen the Z2 to R1 illustrations from Fong, but I wanted to see what would happen if I took the Z3 lattice, which I can visualize, we can see that, we can look at it, and project it down to a two-dimensional plane and see what tiling you get from there. And
you can't get a regular symmetry.
You
can get a regular, of course you can get a twofold symmetry.
Crystal.
Get a twofold, but that's the only one.
Sixfold.
Yeah.
You can get
three, right. You can get three and sixfold and twofold, but you can't get any analog of H2
you
or
don't
H.
have
No.
5.
Right.
It'd just be symmetries of the plane that you're really working with. So like here, it's like a hexagonal pattern. Okay, so the setup here is you have a plane in space, and then you have a lattice. This points to the Z3 lattice. And it's the cubes in that lattice which have their faces. So these are the tiles in the three-dimensional space, which will project down to tiles in the two-dimensional space. And you can change the angle of the plane to get different tilings. And you can shift the plane up and down in space. And it'll touch different boxes in the lattice, and whose ever box touches the plane, they'll have a tile, which gets projected down onto the plane. So here's the tile by itself. So as you push it down, you can kind of see how waves propagate through the tiling.
Depending on the direction the shift vector is going. That's, this is really helpful to get a feel for, for this 3D to 2D case.
He can tell you exactly how he did this. It's really
clever.
Yeah.
You're clever, Dugan. This is really good.
Should do some kind of a game modeling or something.
Yeah.
It's a hypercuber.
Yeah.
Yeah, so
That's
I saw that those waves happen in the Penrose, and then it wasn't until here where I could kind of see like what's
Yeah,
you know,
I really
what's
like looking
behind
at it with the grid when you keep the cubic lattice on, and then it just really drives it all home to under.
Yeah.
Yeah. So yeah, that's what you're asking when you're doing a cut and project. You're asking all these boxes in 5-dimensional space or 6-dimensional space or
Yeah.
what have you. You know, who's got their box touching the plane? Then you just that'll be a
That
tile.
really lets you instinctively understand why some shift vector code on E8 can drive all of our full space of changes in the QSN.
Okay, let's move on to the cut window. Yeah, so if I have a lattice point, and I have his.
Is there any way you can stand on the other side so these guys can see?
Yeah. Okay, so here's your tiling plane, and perpendicular to it is the perpendicular space. If you want to ask, does the cell around this lambda point intersect the plane? The equivalent question to ask is, if I had a generic Voronoi cell centered here at the origin, and I projected that to the perpendicular space, I'd get a volume in that space, and I can just ask whether or not the projected image of lambda falls within the projected image of the projected image under perpendicular space of the Voronoi cell. So this will be some sort of volume metric set in perpendicular space. So for D6 to R3, for instance, your Voronoi, your acceptance window in the perpendicular 3-dimensional space will be like this shape. Mm-hmm. So you have some tiles out there in space, and you project them down to the window, and you ask which tiles fall totally within the window. And this is all folded up. If I unfold it to the parallel space, I get a bunch of OpenGL errors, apparently. This really helped me understand what I was looking at, going back and forth. What's interesting about this?
Looks like a Jitterbug transformation. And it is a Jitterbug transformation,
Yeah.
actually.
You get a lot of symmetry like in the middle.
See? You got your cuboctahedron rotating to your icosahedron. And our angle that we use from E8 is the Jitterbug rotation angle, by the way. Buckminster-Fuller's Jitterbug. So wait, so this is interesting. So you rotate. I just find it interesting, Dugan, that the cuboctahedron is the most complicated 3-dimensional building block of the 20 group, right? Because a 20 group is just it's a compound of 5 regular cuboctahedra, the 20 group.
Oh yeah?
Yeah, if you want to express the 60 points of the 20 group, you take one cuboctahedron, copy it, rotate it relative to our Jitterbug 15.5 angle, and then copy another, rotate it, and so on. And you have then a compound of 5 cuboctahedra, which is the root vector polytope of the A3D3 lattice, so kind of important. And then you've got a 5 compound of it, so you can kind of, in some sense, stay in some algebra of your D3, A3, and then jump, right, from crystal algebra to crystal algebra, right?
I will show this.
A Lie algebra actually is what it would be if it's a FCC. This is very good work, Dugan. I
Thank
mean,
you.
wow, it's really good programming.
Yeah,
Uh-huh.
really good.
And you have not seen everything.
Yeah.
He made a very good programmation of the polytopes.
Yeah.
Yeah.
Yes,
So, working with Z lattice, everything's cubes, and that's fine. But like Z lattice, it's alternated, so you're missing like half the points, and then your root polytope becomes a thing. Your Voronoi cell becomes another thing. A six-dimensional polytope, so you have six-dimensional facets, or five-dimensional facets, and you have four-dimensional subfacets of those. Three-dimensional subfacets and two-dimensional.
Uh-huh.
You get the whole workup, and then scripting the combinatorics for. Actually, it's really pretty simple.
So you're not gonna show anything about D6, right? At least it's not in your slide.
So Dugan, let me give a comment if you're not going to show this. So we saw how Dugan rotated, right? And we saw Jitterbug transform and an infinite set of interstitial positions where one phase was the cube octahedron. This is, I don't know, when I listen to Mike and Alicio and Piero and these guys who have figured out a lot of gauge symmetry physics using Lie algebras, your Lie algebras are connected to your crystal fundamental A, E, D, Z lattices. And so if you kind of take something like D6, if that's the space you want to work in, then you can decompose D6 into some quantity of A3, which is the FCC lattice. So it's inside as subspaces of D6. So anyway, this shape right here is the convex hull of the root vector polytope of the D3 and A3, which is identical in 3D, lattices, which correspond to those algebras that have been used by so many. So there it is. So you see you have the cube octahedron in these 12 vertices. It's a little subspace of the FCC lattice. And then making then here we create 5 of these, a yellow one, blue one, red one, and so on, and we rotate them by the Jitterbug rotation, 15.522 degrees. And what we do is we create a relationship between our fundamental root vector polytope of the A3 lattice and this H3 symmetric space. So then you can kind of know that algebraically you could invent some kind of patterns that allow you to jump from your 5 A3 algebras to the other in patterns, But this representation of the relationship between H3 and A3 is in one object, the 20 group. Whereas when you do the Jitterbug transformation, you really don't have the relationship in the one object. You transform it by this Jitterbug rotation, like Dugan showed, from the cube octahedron to the icosahedron and back. Whereas the interesting thing, at least, about this, and this transformation is what we find in E8. Because if you go into E8 and you arbitrarily select one of your A3 subspaces of E8, where A3 is FCC, and then you take the root vector polytope of that subspace, and you ask, all right, well, here's one tetrahedron I arbitrarily selected, and I want to know, well, what's the angle between that tetrahedron in E8 and a kissing tetrahedron where the kissing one shares a face but is rotated into the fourth spatial dimension in A4. And that angle is the Jitterbug angle. That's the angle, that's one of the fundamental angles that composites to our hypervector that transforms E8 to H4 and H3. So it seems to me that there's this beautiful relationship between the algebras and lattices of the crystal set, and then this, and the fact that I find it surprising, and I wouldn't have guessed that you get that H3 related algebra, H4 related really, in a crystal like E8. Like it's in there, but you got to go down to a subspace and the relationship between the three simplexes to find that angle, arc cosine 1/3, which is 3 pi minus 1 over 4, you know, and the arc cosine of that plus arc cosine 1/2. So that's arc cosine 1/3. So it's hiding in there. But nobody's ever decomposed arc cosine 1/3 into that analytical expression. I don't suspect before us. So we found that the jitterbug angle, in other words, hiding in arc cosine 1/3 inside of E8, and then we exploit it through how we do compounding, where we take that jitterbug angle, which is in E8, and we force an object that has your A3 symmetry locally plus your H3 symmetry globally.
And this is, you mentioned D6.
Yeah.
So D6, have you tried relating it to E7?
Mm-mm.
Yeah, there's a relationship.
I mean, there's a relationship because E7 is composed of sublattices 6, 5, 4, and 3, but I don't know of any.
Yeah, Lie algebraically, SO12, D6, E7. So that's you can split it up. So this is a rotational symmetry that pops up in E7. So there may be a relation, because what's nice about the E7 is the fundamental representation is a 56.
Ah. Huh.